This material has a yield stress. Again, we'll get into the definition of that. Yield stress of 50 KSI or 50,000 PSI to take it into base units. The thickness, or the into the paper dimension, is 0.5 inches. We want a factor of safety of at least 1.5 in our material. We want for each section of this how thick it has to be, H1 and H2, to the nearest eighth inch. Like we discussed, the two sections A, B, and B, C have different internal loads. Every time we have a change in internal load, whether it's moment or shear force or normal force, we need a separate free body diagram. We're going to continue this once we get to chapter 4 and 5. We're going to see the same thing. Or when the torsion changes from one section to another. If we drew the free body diagram cutting anywhere between A and B, that normal force is exactly the same. They all on the, if we, well, I'll just draw it here. For any one we draw, we have 30 kips to the left, and the internal force, I'll call it PAB. It doesn't matter if we cut it here or here or here or here. That force does not change through the length of bar AB. I'll draw in 3D here. The depth is 0.5 inches, and the height we're going to find H1. But we see in our second free body diagram, if we cut somewhere between B and C and we take everything to its right, we have, this one sees both of these applied loads, the 30 kip, a 15 kip, 15 kip. So you see from the free body diagrams, the internal loads are going to be different in each of our sections. For the internal force in But in section BC, the internal force goes up to 60 kip, or negative 60 kip, also in compression. Right, we know the internal loads. We're almost ready for the stress part. There's a factor of safety here, so let's look at that calculation first. The factor of safety we want to be 1.5, or at least 1.5. The materials are the same. They both have that same yield stress of 50 KSI. That's when the material actually will fail due to yielding. Again, we'll get to that next week. But that is what goes on top. The 50 times 10 to the third PSI is when it actually will fail. The denominator is the stress we're going to design for. Divide the 50 KSI by the 1.5. We're going to design it to be able to handle a normal stress of 33.3 times 10 to the third psi. We have to use P over A to find the normal stress for this axial stress that we're going to have here. So the internal normal force is PAB. And for right now, I'll just call it area AB or capital AAB in general. For this material, we're going to use our design stress, 33.3 times 10 to the third psi, is equal to, in PAB, I'll come back in a minute and explain what I'm going to do. The internal force is negative 30 kip, or negative 30 times 10 to the third pound. As you said, the area, the cross-sectional area, is going to be the height times the, I'll call it the depth here. So 0.5 inches times H1. This will be in inches, this will be in inches, so we'll have pounds per square inch, or PSI. Here I need to be cautious because the internal force is negative. I wrote this as positive, but that's, if it's positive, it's in tension. I know it's in compression, so I want to also make this stress negative. Right, that way, this is compression, this is also compression. We're going to assume that this yields the same, it doesn't say, but assume it yields the same in compression as it does in tension. That way, we should get out of this a positive value for H1. I'll do this and then go back for questions. The only unknown in that equality is H1. Assuming that the math is correct on this one, H1, we should get 1.8 inches. So if the height is exactly 1.8 inches, then the stress, the normal stress, should be exactly 33.3 KSI. So H1, 1.8 makes exactly 33.3 KSI, which makes our factor of safety exactly 1.5. But does the 1.8 answer the question? Right? It does not necessarily, unless it happens to be to 1/8 of an inch. We want it to the nearest 1/8 of an inch, and the same idea we used in the last problem, that we're going to want to err on the side of making it the cross-section too large rather than too small. So 1.8 inches is not exactly a multiple of 1/8 of an inch. So what we can do is we can multiply this by 8 and express it as a fraction over 8. So 1.8 times 8, it'll give us 14.4 over 8. And what we can do is if we want to err on the side of slightly too large, I'm going to round this to the nearest whole number. Now I can put this as a mixed number, which is probably how we would order the bolt, or order the height of it. That's going to be the same as 1 7/8 inches. Or as a decimal, 1.875 inches. So you see it's not the same. We can't just round it up to 2 inches in this case. If it was the nearest inch, we would. But if it's nearest 1/8 inch, 1 7/8 is the closest 1/8 of an inch to 1.8 inches. So quickly on the other one, if we want to know the stress in BC, we need to know the internal force in BC over the area of BC. Same idea as before. We're going to use our design stress on the left-hand side, negative 33.3 KSI. Internal force in BC, it was negative 60 kip. And the area of BC, I erased it, but it was going to be its depth of 0.5 inches times a height of H2 inches. .6 inches will give us exactly 33.3 KSI as our stress. But same idea as before, we need to go to the nearest 1/8 of an inch. If I multiply 3.6 by 8, I'll get 28.8 over 8. Round the numerator to the nearest whole number so that this will be in whole 1/8 of an inch. And this tells me that the H2 to the nearest 1/8 of an inch will be 3 5/8 inches.